Good evening to one and all present here. On behalf of PG and Research Department of Mathematics, DG VAISHNAV College, I welcome all the CSIR aspirants. Prayer is simply talking to God like a friend and should be the easiest thing we do each day. Now, Tamutai Vatu followed by college prayer. This is C4 workshop, chase, crack, conquer, CSIR net, which will make the CSIR aspirants to go to the next level. Today, our resource person is Dr. K.A. Venkatesh, Adjunct Professor, IIIT Bangalore, Professor of Mathematics and Computer Science, Myanmar Institute of Information Technology, Myanmar. Now, I hand over the session to you, sir.
Thank you. Good evening to all. I hope you might have prepared certain things. Last week, whatever we discussed, sorry, not the last week, 2 weeks before we met and we discussed graphical method to solve LPP, the linear programming problem. As I said, today I'll start with some questions so that you can participate the questions, then we know preparation also on track. So with that, I'll start. Then I'll go for the new concept with two variables only, called as postmortem analysis. We have a different name, so I'll go with that agenda. Now I'll share my screen. I hope you are able to see my screen. Yes, you are able to see my screen.
Yes, sir. Visible, sir.
Yes. Okay. Right. So all the participants, if you have a mobile, please open the a link. Like last week we did pollev.com/venkatesh.ka647. Okay, so therefore, just quickly what we did the previous week, just 2 minutes, 3 minutes I'll spend on that. We have seen what is the use of mathematical modeling. So we did mathematical modeling. Then subsequently we used the LPP for two variables, how to solve a two variable problem. What is the meaning of constraints and what is the meaning of objective function? What is the meaning of controllable variables and uncontrollable variables? Then we talked about constraints are binding. Then we said why it is not binding. That kind of analysis just we did with that. The information was little more than what is normally talks in the textbook, but it is needed when this kind of examination when you take, you should know thoroughly. Therefore, today also we are going to restrict ourselves to two variable problem only. Right? So this is the first question. Please go to that poll. Then you start answering it. Every question I'll give 1 minute, exactly 1 minute. Then we can go for it. So you are able to see my screen. So what is the question? Constraint in an LPP model restricts value of the objective function, value of the decision variables, use the available resources, all the options, none of the above. So somebody is giving answers. We'll see. This time, as I said, 1 minute, so we have time. So somebody is changing it. You can play around it. But what is the meaning of that? What is the constraint? Suppose the constraint changes, will it have an optimal value? Okay, that I'll say a little more. Meanwhile, see, LPP consists of an objective function. Then we have set of constraints and non-negative restriction. Because of non-negative restrictions, we go to the first quadrant. Then what is constraint? It is some restriction. Suppose you relax the restriction, it is going to be a single equation. So no constraints, it's a single equation. We may not solve it in the usual sense, different values. Obviously, that itself says that LPP, constraint of LPP obviously restrict the value of objective function. So the value of the objective function, the moment you say objective function without decision variable, you cannot see, therefore decision variable is also there. How do you frame the constraint? The constraints are framed based on the available information. What is available information? Suppose if you look at the product mix, so the resources available, how much you can utilize, how much time you are spent on machine 1 or machine 2. Therefore, the option is supposed to be all the above. Unfortunately, it was 45. So that's the reason I said we'll do two variable problem itself more precisely, then we can go to the next one. So the correct answer is D. So all options in the sense except the last one. So value of the objective function, value of the decision variables, use the available resources. So please take care of that kind of things. Slowly we'll go to the numericals. Probably we do better in numericals. I'll move to the next question. Yes. Okay. Constraints in an LPP model represents. So now it is appearing for you. You can see that. And 1 minute I'll give you. So what is the restriction? In the sense, I cannot use more than certain things, or I supposed to use at least. So what is the requirement? You have to take care of that. Balancing, you have to see that. So obviously, so limitation is right, constraints, but represents, it's not only limitations, it is not only the requirements, it's both. So obviously the answer 55%, majority of you have chosen the right one. Okay, there is a change running over here. So I'll move to the next one. While plotting, okay. While plotting constraints on a graph paper, terminal points on both the axes are connected by a straight line because of the resources are limited in supply. Objective function is a linear function. The constraints are linear equations or inequality, all the options. So the resources are limited in supply. Yes, that is one way. While plotting constraints on a graph paper, terminal points on the both axes connected by straight line. So objective function is linear, the constraints are linear, inequations are inequality. So everything is important because we don't have unlimited supply of resources, therefore limited. Objective function, we are calling a linear programming problem. Obviously objective function should be a linear function. The constraints, obviously it is linear, it may be equal or inequalities, therefore the correct choice is all the options. D is the right choice. So majority taken the 64%. So please read, take time, especially any examination, spend little more time than by grasping the question and all those things. Read twice before answering it so that we won't commit mistakes, because there could be we might miss out certain points. So here itself, it's an indication where majority of you taken 64%, which is correct, but the most appropriate answer, expected answer is D, all the options. So that is what you have to look at that. So I'll move to the next one. So constraint in an LPP model becomes redundant. Two isoprofit lines may be parallel to each other, or the solution is unbounded. This constraint is not satisfied by the solution values, none of the options. So redundant, what do you mean by redundant? So what do you mean by redundant? If I remove that redundant constraint, my optimal value is not going to change. So the constraint is, therefore we cannot say none of the above option cannot be said. The constraint is not satisfied with the solution values, we cannot say. The solution is unbounded, because one is unbounded, obviously it is also going to be parallel lines only. Redundant in the sense it's parallel, so obviously we cannot say unbounded also. So the left out choice is two isoprofit lines may be parallel to each other. So when redundant, the meaning is it's parallel to each other. So obviously we can remove one. So the only one choice is available, that is option A. Two isoprofit lines may be parallel to each other. So you should know this is the way you have to find out. So the next question, if two constraints do not intersect in the positive quadrant of the graph, then. So the first one is, the problem is infeasible, the solution is unbounded, one of the constraints is redundant, none of the option. So what happens? 50-50. Okay, look at this. Do not intersect the positive quadrant of the graph. So what do you mean by that? Two constraints do not intersect the positive quadrant of the graph, in the sense it is x1, x2 greater than or equal to 0, is satisfying or not, it is a question mark. So it is not intersecting, in the sense no common area. If it is, even if it is if intersects, it's a common area. If it is not intersect, there could be two possibilities. One is disjoint region. So the moment you say disjoint region, what happens? The problem is infeasible. So that's the way you have to look at that. Just imagine it does not intersect. So both curves are different. So obviously you're having not in the first quadrant, it is intersect, do not intersect in the positive quadrant. So obviously the answer is infeasibility. So look at that, then you have to choose it. Okay, I'll go to the next one. Alternative solution exists of an LPP model when one of the constraint is redundant, objective function equation is parallel to one of the constraints, two constraints are parallel, and D, all the options. So we have seen that a lot of LPP models, there could be more than one optimal value. How it is possible? Suppose if you say constraints are redundant, I can remove, I'll get the same answer. So that may not be there. So next is objective function equation is parallel to one of the constraints. So what do you mean that? So that could be possible. The two constraints are parallel, that is similar to redundant, so we can remove that. So obviously the answer is B, objective function equation is parallel to one of the constraints. So the answer is B, the right choice is B, not the C. So look, please, you have to go through it, read, understand, then you can get the things well. So this I'll give you 2 minutes. You have mathematics normally without pen and paper, or if you are having a tablet and other things, you will be using some kind of pen and paper mode and find out the value of this. The objective function of LPP model is 2u plus v. If u equal to 20, v equal to 30, the value of the objective function, yes, at least yes, so there is no need of talking about, just substitution. It gives us 3 into 20 plus 2 into 30, 60 plus 60, 120. So there is no discussion on this. So now you have to look at this. Now you understood why I asked this question. Today's is we are going to talk about this similar kind of things only, right? Now for an LP problem, minimize z equal to x1 plus x2 such that 5x1 plus 10x2 less than or equal to 0, x1 plus x2 greater than or equal to 1, x2 is less than 4, x1, x2 greater than or equal to 0. So what is the answer? So no solution is possible, bounded solution is possible, there are infinite solutions, none of the given choices. So if you look at this way, what is the first line? You draw the line 5x1 plus 10x2, so you get one chord. So look at the things 5x1. So what line you are going to get? x1 plus x2 greater than or equal to 0. Both you take it as that is supposed to be. Let me see the correct question I given it, or 5x1 plus. Yeah, that is supposed to be okay. There could be an error. 5x1 plus 10x2 less than or equal to 10 supposed to be there or not. I'm not sure about that part. So, but therefore, this problem, if you look at that, it is going to become as when x is equal to 0. So obviously 0, 0, both are going to 0, 0. There is some error is there in the question. I'm sorry about that part. The right hand side has some different value. The first constraint. So I'll skip this question. Okay. Now, okay, this LaTeX did not work precisely. I'll read for you. Minus x1 plus x2 less than or equal to 1 minus x1 plus 3x2 less than or equal to 9 defines. So please draw this line, then try to answer. So people are fast enough. So both A and C, A and B is the right choice, because when you do this, it is going to be bounded feasible region, unbounded feasible region. Both is possible. How it is possible? Okay, now it is going to give us unbounded feasible region, because one goes from this side minus 1 x2, that is next one is minus x1 3x2. What are the points? If you look at that, it is unbounded feasible region is the right one. It is not bounded feasible region. It starts from we've forgotten that positive quadrant, x1 x2 greater than or equal to satisfies. Left side is not closed. It is not closed. It is bounded but not closed. Therefore, it is going to give us unbounded feasible region. So it's going to give us unbounded feasible region. I'll move to the next one. Consider the LPP 3a plus 3b such that 2a plus 4b less than or equal to 12, 6a plus 4b less than or equal to 24, a comma b greater than or equal to 0. Find the optimal solution and optimal value. Okay, now I have to talk about what is optimal solution. The value of A and B is called as optimal solution. On substitution, when you do that, we'll get something. So this is going to be optimal value, A equal to 3, which is satisfies both kind of constraints. You have to see that. Okay, somebody put, I'll verify it. 3 into, so 6 plus 12, so it is not satisfying. B is not satisfying the first constraint. So what do you mean by optimal solution? Which should satisfy all the constraints, then it has to optimize the objective function value. So still people are not doing the right way. Okay, I have given the value, so it is easy. Suppose if I take first one, the second one I verified it 3 3. Suppose if you take 0 and 3, 0 and 3, it is going to give us only 9. Therefore, it is, even though it satisfies, it is not. Now 3 3 comma 3 is not satisfied, so this is wrong. So the possibility is only one choice. A is 0, B is 3, which is going to give us 13.5. So you have to see that 3 into 3, 9. It's going to give us that's supposed to be 13.5 in the sense it's supposed to be A is supposed to be. How many of you solved it? A is supposed to be here, that is 3B, so 1.5. This value is supposed to be 1.5, then only it works. I'm selecting a pen. Somewhere it is writing. Oh, so my touchpad is not working for, unfortunately. This is going to be 1. A, the last choice supposed to be A is 1.5 and B is 3. Then you'll see that it works. So satisfies all the constraints. So choice is this one. The next part is, if the objective function is changed to 2A plus 6B, what is the optimal value, optimal solution? So as I said, because this problem is error, therefore this you can solve it and take this as this two problem as practice problem, then solve it, keep the solution. So how without solving we will find the answers? That's supposed to be the discussions of the day. So it is not the correct answer because 2A plus 6B, so it is going to give a different answer. So if you solved it, if you drawn the graph, at least this part you might have got it precisely. How many corner points or the boundary points are there? Answer is supposed to be 4 corner points, not 3. So it's supposed to be 4. So that's what we have for what we discussed in the previous session. Some 14 questions or 13 questions I put inside. So now we have to talk about what is postmortem analysis, how it is we do mathematically. So without computer software, how we can solve and find out, that's a discussion. So that is very important. It is called a sensitivity analysis. Why do you require the sensitivity analysis? If you look at that, suppose one of you or your company is producing jam, that is the mixed fruit jam. The price of the fruits is vary every day, but the quantity is supposed to be same. The ingredient he can vary so that the taste remains same. Dynamically you have to change certain things. That is what sensitive analysis. We cannot keep one solution, we can work on that. So how to do that? So how graphically we can work it out? So this is very fundamental concept of slope is known to us, then we can do that. So how to do that? Then what is the meaning of sensitive analysis? Where it is going to happen is, suppose my price, I said unit price vary, or unit price vary in the sense increases, decreases, what will happen? Or my available resources is today little lesser than the previous day or little more than the previous day. How we can get out of the solution without solving as a new problem? Suppose for example, if you take 5x1 plus 6x2, one of the objective function coefficient is changed. That is, instead of 5, I got 7. What will happen? So it is permissible. So how to find out? That's what today's class discussion. So please understand, we are going to change 2 quantities. One is coefficient of the objective function. The other one is right hand side of the constraint. Is it clear now? So one is the coefficients of the objective function. Number two, right hand side of the constraint. So these are the coefficients values we are going to change. How much you can change? That is first question. If I change it, what will happen? How much it is going to affect my optimal solution as well as optimal value? That is what. Now you look at this part, two variable problem. I have two coefficients corresponding to the objective function. Can I change both coefficients simultaneously? So one coefficient changes, what happens? Simultaneously, if I change, what happens? That is one side. That is with respect to objective function coefficients. Right hand side of the constraints, you may have 1, 2, 3. How many constraints? We know. The same question be applied here. But the constraints on solving we classified into two categories. One is called as binding, non-binding. Suppose a constraint is non-binding, if I change something, it is not going to affect me. Therefore, you should know when you go for right hand side constraint, this sensitivity analysis will talk only with respect to binding constraints. So what do you mean by binding? The left hand side value plus right hand side, what do you mean by left hand side value is, suppose the constraint is of the form 3x1 plus 4x2. For some values of x1, x2, I got an optimal value. When I substitute 2 and 2, if I take 3 into 2, 6 plus 4 into 2, 8, 6 plus 8, 14. My right hand side coefficient is 14 and 14. This is called as satisfying exactly. Because it is less than or equal to, you should not say this is less than, therefore it is satisfying. It is not. Exact value matches, then we call it as binding. Otherwise, we call it as a non-binding constraints. So now we have non-binding constraints, nothing happens. So don't worry about that. Only binding constraints this discussion. So once again, I'll say objective function is concerned, only two possibilities. If I change one of the coefficients of the objective function, how I can compute the optimal value without resolving the new LPP. Simultaneously, if I do, how can I do with respect to objective function? When it comes to the right hand side of the constraint, I'll be having two. Only one is, if I binding constraints, if I change one of the right hand side coefficient, what happens? Or simultaneously, if I do, what happens? So those who are familiar with Java, nicely discussed. The same thing I'm going to use. I'm not going to use revised simplex method or simplex method. So two variable problem only we are talking. So we restrict ourselves with respect to CSR as concerned. Two variable problems with respect to LPP. Okay, so I'll move. So the sensitivity analysis is nothing but post-mortem analysis. After finding optimal solution and optimal value, one has to perform. So there are software packages. Our LPP, I use Excel. So I can give from Excel, I can give you, I'll show you just quickly, I'll run through what is Excel, how can you do that part also. So what is, we are going to talk about that. The computer output, whatever you have, or sometimes the table is given, how to find out it. So normally we test our students based on the output we'll give, based on that we'll ask them to write instead of asking them to solve a big way. So in general, any solution in this case will have optimal value, coefficient of range, that is we call it as computer output is concerned, range of optimality. Then what is optimal value? Then reduced cost, last class itself we discussed about that. The amount of slack or surpluses, the dual price, the right hand side range. So this slide, whatever I written over here, it will be given enough information in this session. Now in the session, objective function value, that is what we are going to call it as optimal value. Values of decision variable, that is what we are going to call it as optimal solution. Then reduced cost, slack and surplus. Slack in the sense, what do you mean that? There are some unused resources are available, how to utilize it so that in order to benefit that. Surplus, we have excess quantity. So how to surplus, so we have to work on that. Change in the coefficients of the objective function, changes in the right hand side. Please look at these two lines. Changes in the coefficients of the objective function, changes in the right hand side value of the constraints. So this is what we are going to talk about, sensitivity analysis. So now, sensitivity analysis, its other name is post optimality analysis. is used to determine how the optimal solution is affected by changes within the specified range. Only two, the objective function coefficients, right hand side values. So this is very important when dynamically, when we are doing it, the solution is, because nothing is static. So obviously every day you have to work. If you are good at that, you might have done. If I had another 5,000 rupees, I would have bought this one. If I had this price is less than this much, I would have bought one more item. That is what we call it as, in the computer terminology, what if analysis. This is one. The other side of what if analysis is, I have to get after 5 years this amount of salary, I'll work towards that. That is called as goal seek. So goal seek and what if analysis looks similar when you solve it, but it is not. So if I change, what happens now? If I change after some time, what is going to happen? This kind of what if analysis. Goal seek, you fix the target, then work towards that. So with a given scenario, both can be achieved with Excel. In the Excel, you have wizard for what if as well as goal seek. So you can work around that part. So now this is a problem, 5x1 plus 7x2 such that x1 less than or equal to 6, 2x1 plus 3x2 less than or equal to 19, x1 plus x2 less than or equal to 8, x1, x2 greater than or equal to 0. You are familiar with solution of a graphical thing. The first one is going to become as just a straight line, x1 equal to 6, then 2x1 plus 3x2 equal to 0, you put x1 equal to 0, solve for x2, you'll get a value, 2 points, find 2 points for the second constraint. The third constraint the same way, draw the line, identify the common region, find the corner points. Among the corner points, one corner point will be having optimal solution. So I'll put that. So I solve the problem. So I can put this one directly, graphical solution. So x1 plus x2 less than or equal to 8, that is 1. So x1 equal to 6. So the corner points are known to you. The output is, please note down the output. Output has two. One is optimal solution and as well as optimal value. Please note down, this problem is needed. We are going to talk about this. So now x1 is 5, x2 is 3. The optimal value is 46. Now, what is the coefficients of objective function? 5x1 plus 7x2. Then right hand side, what you have, 8, 6, 19 you have. When you solve this way, can I find the binding or non-binding? Yes. How to find out? Look at this, x1 equal to 5. Look at the constraint, x1 is less than or equal to 6. It is not exactly 6. Therefore, this constraint, x1 less than or equal to 6, is not binding constraint with respect to the solution. Now, go to the second constraint, that is, okay, this one, 2x1 plus 3x2. Substitute the values of x1 and x2. So 2 into 5, 10. 3 into 3, 19. Exactly, I have 19. It's a binding constraint. When I go to the last constraint, x1 plus x2, x1 is 3, x2 is, x1 is 5 and x2 is 3, 8 and 8. So except the first constraint, the constraint number 2 as well as 3 satisfies exactly, therefore it is binding. So now, what is that? You have 6, but you are utilized 5. So there is a slack. So we have to think over it. So there is a slack. So what do you mean with that? Some unused resources are available. So if you know, come from the mathematical modeling from the real world problem, then you know what is the 1 unit is we are wasting or not. So that's supposed to be known. See, this is going to give us a nice thing where you can understand better when the modeling is concerned. Now, as I said, how to find a range of optimality for each coefficients provide range of values over which current solution will remain optimal. So now what is our idea is changing one coefficient of the objective function, whether the current solution is optimal or it is going to get affected. What could be the range? So that's what you have to find out it. So this is very important while implementing. When you are on the job, this is what you'll be doing it, not finding solution alone. So how far my solution is sensitivity? If you are, most of you might have done numerical analysis. The same concept we talk in the system of solution of system of simultaneous linear equation. When you do that, we say that matrix norm is nearly unity, system is well conditioned. So what do you mean by well conditioned? So the same way, if I modify small coefficients, either the left hand side or the right hand side, how much it is going to affect, that is what we are going to look at that. So the sensitivity analysis in numerical methods we talk about in terms of well-conditioned systems or ill-conditioned systems. So depending on the book, it talks about that. The meaning is one and the same. Here also we are modifying small values. So what is that range? How to find out it? That is what important. Now, this geometrically what you do, without affecting this, change the slope of the objective function, then you can see that is a place. So now, suppose you take a, normally we write objective function as hyperplane. So what is hyperplane? Any linear equation 2 variable represents a straight line. Any linear equation 3 variable represents a plane. So beyond 3 variables, the general name is hyperplane. So now 2 variable, so it's a straight line. So obviously we are going to have a slope. So general way of writing LPP is maximize z equal to c1 x1 plus c2 x2. So now this is, you have c1 x1 plus c2 x2. What is the slope? So use this, write this equation as y equal to mx plus c, then you are able to get the slope. So now changing the slope of the objective function, what do you mean by that? How to change it? Just move the isopropyl line. If you move without affecting the feasible region, so there could be a changes. So that is what we are going to, how much you can go for it, that is what we are looking at. All right, so look at this. The slope of the objective function line is maximum c1 x1 plus c2 x2 is minus c1 by c2. The same way, the constraint, if you take a1 x1 plus a2 x2 equal to b, that slope is minus a1 by a2. So you can find out, we are just writing the y equal to mx plus c form. From there you can find out the coefficient of x is the slope, you can pull it out. So using this only we are going to find out it. Some inequalities we are supposed to talk about. So that inequality will come automatically. So how it is going to happen, you see. Now, range of optimality for C1, what has happened? You take one of the binding constraints. What are the binding constraints we have? Constraint number 3 as well as constraint number 2. So in this case, first I consider the binding constraint x1 plus x2 equal to 8. What is the slope of that? That is minus 1. Slope of the constraint is minus 2 by 3. So now you have, so first coefficient value, what was the objective function? 5x1 plus 7x2. So I want to find out how much I can increase or decrease my values of C1 without affecting the second coefficient, that is 7. So that slopes always lies between two binding constraints. So minus 1, that is the first constraints things, less than or equal to minus C1 by 7. That C2 value is, the coefficient value is 7. So minus 2 by 3. I'm not substituting the value 5. If you put 5, there is nothing can be dealt with. Therefore, how much the Ci can vary, C1 can vary. So now in order to do nicely, we multiply. So this is, when you take multiply with minus 1, the inequality get reversed. So obviously you got 14 by 3 C1 less than or equal to 7. 14 by 3 less than or equal to C1 less than or equal to 7. So this is a wide range. This range can be narrowed down. If you are able to narrow down, you are got really the best solution. What do you mean by that? So this value 14 by 3, how much is it? 4 point something. When you do more iteration way, this value will become closer and closer, so that the effect of objective value, optimal value is not going to be much high. So therefore, one has to work. Then only we can say that the solution is optimal. So this is very important. So you know slope, you are able to find out this way. Is it clear? So now, same way, when I go for, if I change C to how much I can change, I can find out it. So what will happen? This is the place C1 is going to become as 5 minus 5 by C2. I'll put the same range, do the math. So we'll get an inequality, the maximum range and minimum range we'll get. So I got for this optimality for this 5 C2 less than or equal to 15 by 2. So now I know within this range. What do you mean by that? If I increase or decrease, so this left hand side is permissible decreasing value, this is right hand side is increased value. So with that assumption, you have to go for it. So if you solve using a computer tool, the solution gives you a nice picture that is easy to solve. If mathematically, we can solve by hand this way only. Now this is a computer output produced by Excel. End of the session, I'll tell you how to use Excel to find this way. So now look at this. The optimal value is 5.0, 3.0. What is this? That is the optimal solution we have. Our original coefficient was given as 5 and 7. Allowable increase is 2. Allowable decrease is 0.333 with respect to first coefficient. With respect to second coefficients, this is we have. Now, so I said the constraint right hand side is 6. So now the final value was 5. This is 19.8. We have seen because of this only we said constraint 2 and 3 are binding. 5 and 6, there is a slack. 6 minus 5, 1 is the slack. So what is how much you can allow and how much you can decrease. So if this table is given and the problem is given, now the question can be asked. If objective function, the coefficient 5 is increased by 10, what will happen? Now you can see the range. It can go between 2 and 0.33. That is allowable range increases 2. 5 is beyond that. This is going to be the optimal solution is not going to be the same. It's a new solution. So that is what we have to look at that. So we'll go with an example that is better. Now, so we have how to change. We have seen that. Now we have to look at the right hand side how we are going to change. There we'll talk about one concept called as dual price. So we know simplex method, dual simplex method. Now we'll understand what is the meaning of duality. Don't say just duality is maximum right, minimum, less than or equal to right, greater than or equal to. That is key, a working procedure. The real meaning you should know. That is important. See now the improvement in the value of optimal solution per unit increases in the right hand side is called dual price. So 1 unit increase, how much it is going to improve? So that is called dual price. That the computer software gives nicely inside. You multiply that, you'll get this. So the range of feasibility is again where it can go, where it can increase or decrease. So that is possible. So now the last one more time reading it. As RHS increases, other constraints will become binding and the limit the change in the value of the objective function. So that is. So now we know dual price. So what do you mean by that? By adding 1 to the right hand side, whether the optimal solution remains same or not. So that is what we have to talk about. So the dual price is equal to the difference in the value of the objective function between the new and original problem. If you add 19 as 20, then you got a new problem, solve it. What is the dual price? Earlier we had x1 is 3 and x2 is 5. The objective function was 46. When you put instead of 19 and 20, if you solve, you can see that is increased by some quantity. The difference between the original value as well as the new problem solution is called as dual price. So non-binding kind of constraint, we are not going to talk about that. Therefore, it is 0. So negative dual price indicates that the objective function will not improve if the RHS increased. So that is another important note. This can be asked in the true or false kind of things. So this is a relevant cost. A resource cost is a relevant cost if the amount paid for is dependent upon the amount of resource used by the decision variable. So there are certain places what we'll do. No, that in the market also, when demand is more, we are ready to buy more than the normal price. So such time we have to pay. That is also involves a cost. How much you are willing to pay? That also can be identified. For example, today's scenario, the onion prices are 90. Suppose I want a good quality. If I'm ready to pay more than 90, if somebody delivers at my home, how much I'm willing to pay? So that way you can talk about that. So based on your available resources and market price, you can think it of how much I'm willing to pay. Will it still suits my budget? So that's what we have to talk about that. So the sunk cost is not covered by objective function, so we cannot talk about that. So we have to see in the practical scenario is concerned. So as I said, dual price is the maximum amount you are supposed to pay for getting additional resources. So that is very important. That is when you do that way, resource cost is called as sunk cost. So that is important. So resource cost is relevant. You can decide what is the premium over the normal cost you are willing to pay for 1 unit of resource. So this is two, you should know difference between these two, then it is easy to solve the problems. Now, at the same example, x1 is less than or equal to 6 is not a binding constraint, therefore dual price is 0. Now, change the RHS of the constraints 2x1 plus some, what was the constraint? It was 2x1 plus 3x2 less than or equal to 19. Increase the right hand side by 1 unit, that is 20. Now, when we solve this problem, x1 plus x2 is 8 and x1 is less than or equal to 6, that is also there. The objective function is same, 5x1 plus 7x2 subject to 2x1 plus 3x2 less than or equal to 20 and x1 plus x2 is less than or equal to 8. When you solve as a new problem, you will get the value is 48, original value was 46, original problem value, so 2 units it is. So now, what is the meaning of this? It is increased, optimal value increased by 2. If you are using a computer solution, this 2 will appear on the right hand side as reduced cost. How many unit you can increase from the range of feasibility, range of optimality, you can see that, then you can multiply that with this and you can do that. So now constraint, we are retaining second constraint as now as it is. Third constraint we are increasing by 1. Solve one more new problem. When you are solving it, that is increased, the optimal values got 47. Earlier it was 46, 47 minus 46 is 1. So all these are 2 variable problem. Therefore, in the CSR it can be asked for 4 points or 3 points. Somewhere they can ask it to solve it, and or the solution is given, optimal solution is given. When the right hand side is increased by 1, how much changes happen, find the dual price. So for that, this kind of problem is possible. See, now this is what the output produced by a computer. Now you have here 0, 0. We are talking about right hand side increases. Now look at this. Something is called a shadow price. What is that? If I increase 1 unit, what is the shadow price? 2. So original objective function I increased by 1. So 1 into 2, the new objective function, objective value is going to become as old objective function value plus 2. Suppose if I increase by 3, then multiply by 6, add with the old one, you got the new optimal value. So without solving the new problem, we can use this shadow price, provided you got this table, or you have to go the other way. So this is a tricky way. So once this output is needed. Now look at this, how much I can increase. Allowable increase is 5, allowable decrease is 1. The same way allowable increase is 0.33, allowable decrease is 1.1. Even if I increase 1, I got 1 is shadow price is 1, therefore I got 47. So that is the way one can look at that. Now, range of feasibility, I said, determine finding this one. For a change in right hand side value, the range of values for this coefficient original dual price remains constant. So the ranges within this range, I'll go back to the previous slide. What is the meaning of that? I'll say What is the meaning of that? The allowable increase is here, allowable decrease is here. If I do some modification, take the second constraint, allowable increase is 5, allowable decrease is 1. If I modify my right hand side value, instead of 19, I can go up to 19 plus 5, 24. And the same way, left hand side, I can go up to 18. Suppose in between 18 and 24, you change the constraint, how many problems you'll get? 18, 19, 20, 21, 22, 23, 24. So you'll get 5 problems. All the 5 problems, the optimal value is going to, optimal solution is going to remain constant. What do you mean by that? The final value you got 5, 1 and 5, 3, that is going to be as it is. It is not going to change. So please understand. So you have to do that way. This constraint will modify. Right? That is what called as a range of feasibility. So same way, range of feasibility, we talked about that. So this is range of feasibility. Same way, we have objective function coefficients also, range of optimality. So the allowable increases 2, allowable decreases this. Within this range, if I do any changes, the optimal values, optimal solution is going to be same, optimal value vary. So that is what important. Now we talked about right hand side. Same way we have to talk about if I change objective function coefficient, what will happen? So that is the last part, the same way. Now we have one more small problem. First, quickly you can model it. So you take 2 minutes of time, then model it. So what is that? Some bike company has 2 kinds of bicycle frames. One is called as with aluminum, one is called as deluxe, another one is called as professional. So they are producing this 2. So the profits is given. Therefore, once you, the order which you have to do is first identify the decision variable. Based on that, you can identify the objective function, whether it is maximum or minimum, because it talks about the profit. So obviously it should be a maximization problem. Unit price for first one is given as, the deluxe model is given as $10. The second one is given as $15. So you can say that 10x1 plus 15x2 is the objective function. Then the what is given for deluxe producing is aluminum alloy and steel alloy is there. So obviously you are going to have 2, 3. What is that they given? Yes, aluminum alloy is given. So column wise you take. So you'll get 2x1 plus 4x2 less than or equal to supply 100 pounds of aluminum. With respect to second one with column 3 and 2, 3x1 plus 2x2 less than or equal to 80 pounds. X1 and X2 greater than or equal to 0. So the modeling is ready. Once it's a 2 variable problem, model is ready, then we have to convert into LPP, and so LPP is done. Then we have this. We have to solve this problem. So what will happen? 10x1 plus 5x2, 15x2. So whatever we discussed, that same. So on solving it, we'll get some solution. So that's that Excel, how it has been put, that is the same column. Now you have, see, bikes made 15, x1 is 15, x2 is 17.5. Now you think it of this place, I forgot a modeling problem, because the bikes made 17.5, it should not be. So I have to go for integer programming. That I'm not talking now. Therefore, I'm permitting this solution is allowed over here. So LPP as a mathematician I'm looking at, not modeling perspective. So that is, so the maximized profit is given as 412.5, that is given. So both constraints are binding here. Aluminum is also 100, this also 100, 80 and 80. So both constraints are fine. So now using this, we have to infer certain things, the sensitivity analysis. So now, according to that, that is what we talked about. All right. Suppose the profit on deluxe frame is increased to 20. Is the above solution still optimal? What is the value of the objective function if the unit price is increased to, unit profit is increased to 20? So deluxe frame is okay, profit is 20. Yes, the solution is optimal. So what do? You have to identify the slope, identify the range. If this is within the range, answer is yes, otherwise no. Now, what is this? We are talking about the 10 part. We are going to increase as 20, whether it is permissible. So allowable increase is 12.5. So 10 plus 12.5, so 22.5. So it is permissible. So allowable will increase as permissible. 20 is still within the range. This optimal solution remain same as 15 and 17.5. Only the value will get changed. So what is the value will change? So now we know that is going to change it as 20 times 15 plus 15 times 17.5. So because the 20 is lies between these two values, so 10 plus 22, 12.5, that is 22.5. So it is within the range. Therefore, we are multiplying 20 into 15. Earlier we got 10 into 15 plus 15 into 17.5. So this is known. This output is known. We can do how to get these two values by finding the slope. So we have seen that how to find from the binding constraint. For fixing the slope, we need two binding constraints. Here both the constraints are binding. Therefore, we can do this. So what is that? One side 80, then minus C1 by C2. So find out the slope of this line, the constraint and this constraint. Both three slopes you have, put that. So between both constraint slope, minus C1 by C2, that is minus 10 by 15. Then do math, so small part computation, which gives the nice value for C1, allowable increase, allowable decrease. Within that range, we are permitted to operate. So that the optimal value, optimal solution remains same. See, that's what I said. So within the range, so therefore 20 into 15, 15 to 17.5, 562.50. So there is no need of resolving the problem. So this is the dynamic environment. When my price market demand goes up, some price unit price varies. So I can compute it whether it is still in our limits. So that is possible. So now, what is that? If the unit price is decreased, so it was earlier 10, now it is 10 to 6 we brought it, what will happen? Optimal solution changes or not? Because the solution value is 12.5, that is 7.5, so obviously it is possible, so within the range it remains. So now, so okay, 2.5, 10 minus 2.5 is 7.5, so 6, so obviously this. Right, so 7.5, so 6 is within the range, optimal solution, final value is only things. All right. So now, so far what we have seen is within the range, optimal solution is same, otherwise beyond the range, it goes outside. 100% rule, what is the meaning of 100% rule? In the sense, whenever you change simultaneously either the objective function coefficients or the right hand side coefficient, right hand side values, the change should be within 100%, then the optimal solution is valid. Otherwise, we have to resolve the problem. Is it clear now? So instead of doing one, can I do two coefficients at a time? Yes, possible, provided the change supposed to be within the 100%. So how to obtain? We'll look at one more problem, so that the same problem we can talk about that. Now, simultaneously, the profit on deluxe frame is raised to 16. So the range is known to us, up to 20 it is permitted, but 16. The profit on professional frame is raised to 17. Would the current solution be optimal? So what is it originally? 10. 16 minus 10, 6. So that is the change, new change. The maximum allowable increase is 22.5. So originally it was 10. So 22.5 minus 10 is going to become as 12.5. The change is 6 by 12.5, 48% change. So one is 48%. Similarly, we have to compute. Earlier it was 20. The permissible, what we are saying, raised. This is raised. So permissible is 20 minus 15. So this is going to become as 5. 17 minus 15, 2. So 2 by 5 is 40. Add this 2%. So 88. So it is still, it is within that 100%. Therefore, the optimal solution is remains same. The optimal value changes. So how to find the optimal value? How much you reduced, add or decrease. If it is decreased in the final solution. Final solution was 15 and 17.5. Now here we increased 17 also. What this was earlier it was 20. The professional frame was raised to 17. So earlier it was 15. So both are increased. So obviously adding. Otherwise, one addition, one decrease is possible. But the percentage you have to add, you should not do difference. So total change in percentage always less than 100%, then it is possible. So the same way, right hand side, what we can do. So that is also the same way, 100% rule, right hand side, allowable change we have to find out. If it is less than 100%, optimal solution is same. If whatever the changes you are doing it, multiply with shadow price, the number of unit increased or decreased. If it is increased, add it. You are decreased it, subtract it from the optimal value, so that without solving the problem, we'll get the optimal value. So you have to practice many problems. I'll give you some any book, including Taha book itself, Humpty A. Taha book itself have a lot of problems on sensitivity analysis. Suppose if you are looking at little easier book, Taha is the easiest book, or as I mentioned the last session, follow any book, Introduction to Management Science. So that is the book. You'll have a lot of such problems. Look at that. That is fine. Okay. So this is how much one has to pay extra home. So dual price you can compute it. So you can find out that way. So you have the sunk cost can be calculated. So it is 50. So 156.25. Okay. Okay, this is okay. I'll stop here. This is what I said, how to compute it, how much amount you have to pay it, multiply with the range of feasibility. If you are looking at the right hand side, shadow price, multiply the shadow price with the number of increase or decrease. If it is increased, add to the original optimal value. If it is decreased, subtract from the optimal value in order to get it. So that way you can find out it. This. So this is one more problem, because we talked about minimization, maximization problem. Now it is a minimization problem. This is given. When you solve this problem, what is the optimal value? So objective function is going to become as 27. X1, X2 value is 1.5 and 2. Here, reduced cost is 0. The dual price is given something. Slack surplus is how much? So dual price is given. Dual price is negative. What is the meaning of it? This is not going to do with. So now there is another software called as management scientist software. Looks like this. So therefore I put this also. We have no limits. So upper limit, lower limit is there. With respect to objective function coefficient, lower limit is 0. That is current value cannot be reduced. But upper limit is 12. So 6 plus 12 up to 18. We can change it. This lower limit is x2 is 4.5. So 9 minus 4.5, 4.5, no limit, so it can increase like anything, but increase anything hypothetically, but it is not a thing. The same way, the right hand side, if you look at that, lower limit is so 5.5, 15, 30, current value is 30, so upper limit is lower, so 30, 55, 0 to 4. I'll give you my solution in Excel. That would be a better way of seeing it. According to the output, this we have. Now, using this, some changes, what will happen? Suppose the X1 is decreased to 4 units, is the current solution is optimal. What is the value of the objective function when this unit cost is decreased to $4? So now, what is that? X1 is decreased, so we can up to current value is 6. So 4, we cannot do that. So listen, if it is the range, we have to do that. Otherwise, we cannot do within the range 0 to 12. So within the range, the optimal solution will not change. However, the optimal value is affected by, instead of 6, multiply with 4, we'll get this one. Now, x2 decreased without the concept of optimal solution. So now does not fall below 4.5. So maximum is 4.5. We cannot go beyond that. So obviously we cannot do that. So I'll stop here. I'll go to Excel so that you can see how it has been computed, how Excel produces that part. 1 minute. Yeah. So I'll just go to the Excel. The first problem was this: what we had. The Excel solution is, but the sensitivity report gives like this: allowable increase, allowable decrease, 10, 15. See, this is original value 15 and 17.5. Allowable decrease is this much, 8.33. So we have this right hand side. You have seen that two constraints. So 100, 100. So this is what permissible. This is the bike problem. That's what we talked about this. So now when you have this, what happens? This is for when x is 15, 100, 18, so 17.5. We solved it. From that we got this report. So now the first problem, what we have seen, RHS change. Instead of 20, when I solved it, 48, I got it. So the last problem, if I go here, this was the problem: 1.5, 2, 6, 9, 27. Constraint 1 is 1, 2. So 5.5, 8, 30, 30. Now you see here, first constraint is not binding, second constraint is binding, third constraint is binding. So I have this. So what is the meaning of that? Suppose if I increase this quantity, I'll go here, sensitivity report for example 3. Yes. Now, right hand side is 30. What I'm going to do is I'm going to increase right hand side by 10. So the moment I increase by 10, originally it was 30, it is going to become 40. How much increase in my optimal value? Because within the range, so it is 25 is permissible, so 10 only increased. So 10 times 0.6, that is 6. So it is going to become as 27 plus 6, 33. I can find out. Simultaneously, if I do, you have to find the this percentage. Now here, the second constraint also I'm going to increase by, say, second constraint I'm increasing right hand side by, say, 2. So then 2 is possible. So 2 into 4.5, 9. So I'll increase 27 plus 9, 36. So if I decrease, what I have to do is 27 minus 9, I have to do that. So this shadow price helps us to find out this way. So the optimal solution is remains same. The same way here, this table is known. Allowable increase is 6. If I, instead of 6, if I put 10, what I have to do is, originally it was 27. 27 plus 4 into 1.56. 27 plus 6 is 33. So that way I can compute it. The sensitivity analysis is useful when you talk about this kind of problem. So in order to solve, the easiest way is using slope. Two variables by hand, find the slope, find the range. In order to do that, two binding constraints are required. So when the problem is given, two binding constraints are possible. With that only they'll talk about that. Find the optimality range. The same way, find the range of feasibility, then play around it. So we'll be having, and this is the way we can solve the problem. So I have this much. If I'll solve one problem for your benefit, so that you know how I obtain this. I'll take some random values and solve it so that you know how you can use Excel also. So I'll take two variables, calling it as X and Y. This is the place I want to have final value to be stored over here. Are you able to see my screen? Yes.
Yes,
okay,
sir.
right. Okay, I'll go here. I'll put some color over here. Final decision variable I'm going to have here. So I'll write objective function coefficients. I'm going to write, so objective function. Then I'll take some constraint CONS1. Then I'll go for CONS2. Then I'll go for constraint number 3. So 3 constraints I'll take it as. So I'll take some random problem. So I'll take 4 and 7. The constraints, I'll say x1, this is x2 is 0. So 2 plus 4, I can take it as, and constraint 3 is minus 3 plus 10. So I know what is this problem, but just values I'm filling it. So this is 10, and this is going to become as safe 20, and this is going to become as 25. So conveniently, I'm taking all are less than or equal to. So less than or equal to. all constants are taken less than or. If you want, you can put greater than or equal to, then only one place you have to modify. Now, what is objective function? 4 times this value plus 7 times this value. So this is supposed to be, I do multiplication. So I use sum product. There is a function, built-in function in Excel called a sum product. I utilize that. Okay. Sum product. I want this value, comma, then this value. I can fix absolute reference. I'm not doing it. So for convenience, I'm not doing it. So again, I'll do this part equal to sum product so that you also can get accustomed what I'm doing it, you know. Sum product, this into this 2 cells. So I take a net, then here, this is over. So 2 more times I have to do it. Sum product. Sum product. This is a constraint I'm taking it up. So then equal to sum product. So initially all values are 0. The reason is the default value in Excel any cell is 0. Therefore, we got this is the place final optimal value is going to store. So therefore, I put some color over there so that you know what is we are doing here. This is optimal value. This is the decision variable. The optimal solution is going to lie over here. So I'll keep where optimal value is there. Then I go to data. So those who are not familiar with Excel or first time you want to use LPP to solve Excel, what you have to do is go to File, then go to Options. In this Options, and close my keyboard. Okay, this Options add-ins will be there. Once you select add-ins, then you can see that Excel add-ins here. Then you can say go. You'll get many things. Analysis toolpack. So you will be getting only 3: analysis toolpack, VBA, and solver add-in. Since I work other tools, therefore it is we are getting other tools also here. The moment the checkbox is ticked in, that is fine. So then check it, then okay, it will come here. I'll show where it appears. The moment you select it, it appears under data tab. You can see data analysis solver. So my cell is selected, cell is here. I'll go after selecting this cell, go to solver. The set objective function supposed to reside over here, SH3, that is a place it's going to reside. So the objective function you can change it as either maximum or minimum. So now the problem is maximization problem, we assumed it, therefore maximum. So now by changing the variable, like what you do, the feasible solution simplex method goes from feasibility to optimality. The same way it works over here. 0, 0. That is a x1, x2 greater than or equal to 0. Therefore, starting with this. So changing the cells. The cells are initially 0. You have to change the cells in order to obtain optimal value, subject to the constraints. Now the constraints, you have 3 constraints here. Then go here add. Then you will take 3 constraints value the left hand side. What do you mean by that? X1 less than or equal to 10. That is a constraint. Second constraint is 2x1 plus 4x2. So you have only left hand side I have taken. This place is the place if it is greater than or equal to. If you see that less than or equal to, greater than or equal to. Suppose you want to solve it as an integer programming problem, then we have to choose integer. That I'll say when it comes over integer programming. Or the values x and y supposed to take only binary value 0 or 1, then you can choose binary. So that's the way you have to talk about. So now less than or equal to, then the right hand side I'm choosing it 10, 20, 25. The moment I add this one, so this is done with. So I'll go say okay. Now to cancel this one, only 3 constraints are required. So we have 4, 5, 6. So verify it. 4, 5, 6 rows are the constraint row. So this is changing cells. Then you see GRC nonlinear, evolutionary computing, or simplex method. So we'll take simplex LP. I'm solving it. So now I solved the problem. I got some value, x1 equal to 0, 10 and y equal to 0. My optimal value is 40. From here, there are two reports you will be working on. One is answer and sensitivity. Answer is here. If I take sensitivity report, this allowable increase, allowable decrease, then what is the reduced cost, what is the shadow price, everything will appear in the nice form whichever I shown to you. The same way it is going to appear over here as sensitivity report 1. Now we got this. So now you see that x and y final value, this is a reduced cost. Now here any constraints are binding. From here you can talk about 20. This original value right hand side is 20. What is the price? What is the constraint right hand side is 20. Okay, allowable increase is 22, 0, 25. So final value is also 20, 20. So what do you mean by that? It is satisfies exactly binding. This constraint also binding, but not the third constraint minus 30. Here the RHS is 20. So even though it looks satisfying, but it's not binding. So we have to use only these two constraints in order to solve. So now when you are solving by hand, how do you find out binding or non-binding? Because we know the value of x1 and x2, substitute in every constraint, identify whether it is exactly equal to the right hand side value. If it is equal to right hand side, then you can say that it is binding. If not, it is not binding. So play with two binding constraints. Suppose you have only three constraints, two constraints are unbinding. That time definitely we cannot do this kind of exercise. So with hand, by computer solution is only possible. So now you have this value. Now what is the meaning of this? I can increase up to another 22. So if another 22 is 20 plus 22, 42, I can decrease on a, it cannot decrease this constraint. This is one is constant. If I increase by 10, what will happen? The optimal value, what is the optimal value? It was 70. So 10 into 4, 40. It is 40. Sorry, 10 into 4 is 40. Now, if I increase this right hand side by 10, another 10, that is put 30. So 10 into 17.5. So 40 plus 17.5 is going to become as 57.5. So you can find out easily. Suppose here this constraint is increased by 1. So what will happen? The final solution is going to become as nothing because the final value is 0. Can we increase this one? Can I decrease this one? Allowable decrease is 0.5. So 3.5, if I put it, how much I have to reduce it? So whatever the value 40 we had, minus 0.5 into 10, that is 5. So the objective value is going to become as 35. So use this table. Based on this table only, entire computation can be dealt. So because it's an objective type question, so we may not ask three variables. Therefore, I restricted my talk only with respect to 2 variables only. So any queries, any problem to be solved, please send a mail to the organizers. They will send to me. So next week, you'll be having 15 questions based on sensitivity analysis on how we are doing it, so that will test you how far you are also preparing along with us. So that's an idea. It is not to grade you, only to ensure that your burden will be less, because December is not far. You're supposed to go for examination in the month of December. So much before that, at least these 3 questions or 4 questions, whatever appears in the CSCR, you should be thorough with. So, okay. Any queries, you can post on the chat window. Another 15 minutes, I'm available for you. Otherwise, it's monologue. I'm expecting a dialogue from you. Or any other areas, whatever we discussed, you want to revisit, please let me know. Yes, no questions. So Tirmal and others, please help me out.
Sir, still no questions in chat box, sir.
I'm unable to hear.
Sir, in comments, no questions.
One
Still
minute.
no questions, sir.
Yes. Please. Any questions?
No, sir, no questions, sir.
Okay. Audience side, please. Am I too fast? Please let me know so that I can slow down. I assume that you are doing the work, therefore I'm doing little faster. I know that, but that is need.
Sir, one participant said the Excel text only not visible, sir. Remaining okay, sir. Slides are okay. But in the Excel text only not readable. See, sir, one person says.
Okay, just I'll increase the size, probably the percentage they may see it. Let me see. Is it permissible now?
Yeah, now okay, sir.
Okay, I'm sorry. You know, done it earlier itself. So next time when I use Excel, only the increasing the size, I'll take care of that part. Okay, okay.
Okay, sir.
Yeah. Sorry for the couple of questions. There was an error. I would have verified it before serving it. I'm sorry. Next time I'll ensure that that won't happen. Yeah.
Okay, sir. No other questions, sir.
Okay. Then I'll thank the people for listening me. Please practice it. As I requested, please post queries to organizers. In turn, they'll in touch with me. Before next session, you will also get the solution. Okay. Thank you, Tirmal, and thank you for others.
Thank you, sir.
Thank you, sir, for spending your valuable time in our CPO session. Really, it's a wonderful session to all our students, research scholars, and teachers. One must thank the people who made an impact in their life, and our resource person is one of them. Thank you so much, sir. On behalf of PG and Research Department of Mathematics, thanks to our Professor R. Venkatramanan, Head Department of Mathematics, for organizing this C4 workshop. Our next session is tomorrow at 11 a.m. Thank you.